Dear all, hi! In this class we continue speaking about mixture models, but now we move towards Poisson mixtures. From a conceptual point of view, the difference is very simple. Instead of Bernoulli's, we are now dealing with Poisson random variables. The practical implication of this change is that in principle a company may now default more than once. How can we justify this? If you think there is a simple example, and it's the case in which a company defaults, the shareholders bring new capital in order to save the company, but this new capital is not sufficient to avoid a new default in a very short period. With y tilde, we indicate the variable counting the number of defaults for company I. Given the random factor vector psi, we assume that the number of defaults for each company is a Poisson random variable with rate lambda I of psi. We can then define a new variable m tilde that corresponds to the sum of all the y's tildes. It is interesting to notice that when the lambda i's, that is to say the Poisson rates, are small enough, then m tilde is a very good approximation of the m we have seen before in Bernoulli mixtures. In probabilistic terms, m tilde is the sum of conditionally independent Poisson variables. On screen you can see what I mean. If we define the random variables zi indicating the events at least one default for company I, then we are back to the old framework we have seen, and pi is equal to 1 minus the exponential of lambda I of psi. Credit risk plus was introduced by Credit Suisse Financial Products in 1997. It is a Poisson mixture model in which the common factors are p independently distributed gamma random variables, and this assumption essentially allows for the derivation of closed form analytical results, and from a computational point of view it allows for the use of very strong tools coming from actuarial mathematics like the so-called Panger recursion. Now, I have to admit that within the class of credit risk models, Credit Risk Plus is actually one of my favorite ones. In the model, we assume the intensities lambda I of psi to have a linear representation of the form Ki Wi psi, where Ki is a non-negative constant, an important one we will see, and Yi is a vector of convex weights. We assume the vector psi to contain independent gamma distributed factors with parameters alpha j and beta j, j from 1 to p, equal to the inverse of the factor variance sigma j squared. We assume this quantity to be observable from data. The choice of gammas is due to two different reasons. First, their flexibility in terms of shape, and second, the possibility of obtaining closed-form analytical results, as we will see in a minute. Thanks to this parameterization, we have that the expected value of each factor psi I is exactly equal to 1, while the variance is the sigma squared j we were assuming to be observable. Moreover, if we consider the expected value of every lambda I, this expected value is exactly Ki, and this is very interesting from a computational point of view, as we will see in week 5. What is interesting is that the quantity Ki can be essentially computed on the basis of historical data. The default probability of counterparty I corresponds to the probability of observing at least a default for I. This quantity can be easily and satisfactorily approximated if we assume the values ki to be small enough. Now, since we know that the Poisson distribution is closed under convolution, the conditional distribution of m tilde is still a Poisson, whose intensity is the sum of the intensities of the counterparties. For the derivation of the unconditional distribution of the approximate number of defaults, we can use the properties of Poisson-Gamma mixtures. This is a popular result from actuarial sciences, which tells us that if a random variable N has a Poisson distribution with intensity lambda, and this intensity is gamma distributed with parameters alpha and beta, then n is a negative binomial. The proof is simple, and you find it here if you are interested. If we assume to have only one common factor, then the negative binomial result can be immediately applied. In the general case with p factors, m tilde will be a sum of p independent negative binomials. This follows from the fact that we have assumed independent gamma distributed factors. The computation of m tilde can be performed using a very interesting tool known as Panger recursion, which allows for an efficient iterative procedure. For the moment, it makes no sense to enter into the details, but we will be back in week 5 with a working example. We will see that Credit Risk Plus is fast and requires only a few input data, typically easily observable. It's all for the moment. See you next time. Thank you and goodbye.